All right, section 13.4. This is the last of the sections in chapter 13. We're going to be talking about motion in space, specifically velocity and acceleration, and some of the things that go along with that. So we're actually going to be talking about velocity, acceleration, the speed, something which is called centripetal force, and the tangential components of velocity and accelerations. So for those of you guys who are really into the physics, this will be a good unit for you. It's not an incredibly difficult unit, but it will take a little while to get through everything. Probably have 3 videos on this one when we're all done. All right, so let's go ahead and get started. So again, we are talking about motion, which is going to be velocity, which is our R of t. I'm sorry, not velocity, position, R of t, velocity, V of t, and acceleration, A of t. All of these are vectors, which means that they all have direction and magnitude. Direction, magnitude. All right, and as you would expect, just like velocity, position, velocity, and acceleration in 2 dimensions, in 3 dimensions, it's the same basic principle. The velocity is the derivative of position, how the position is changing. And the acceleration is the derivative of velocity, how the velocity is changing, or the second derivative of the position. And then speed, speed is the magnitude of the velocity. And because it is a magnitude, this is a scalar. So the speed of all of those things is a scalar. Okay, so let's go ahead and find the velocity, speed, and acceleration of the given position function at the time t equals 1. So let's go ahead and find, I guess we'll find velocity first. That makes the most sense. That is going to be the derivative, which is going to be 2t 1. Okay, we want to find the velocity at 1 because it says at time t equals 1. So we'll just plug 1 in there and we're going to get 2, 1. Then we want to find, well, it does say find speed next, but I'm going to find acceleration next. It doesn't really matter the order there. So the acceleration is going to be the derivative of velocity, which is 2, 0. We want to find the acceleration at time t equals 1, which is also 2, 0. So as you can see, your acceleration is actually not going to change there. And then the speed. Speed is the magnitude of the velocity. So magnitude, remember, is each component squared. So that's 2t squared, so that's 4t squared. 2t quantity squared plus 1 squared, which is 1. And then we want the speed at time t equals 1. So plugging 1 in there, you're going to get 4 plus 1 underneath, so you're going to get root 5 for your speed. And then obviously you'd have units to go with that. Let's go ahead and take a look at what this looks like. Now obviously this is a 2-dimensional vector. So this would be something where it's just pretty much sitting flat on the xy plane. Could obviously create a 3-dimensional vector out of all of these just by putting a 0 for the z components. It just means, again, it's sitting flat on the xy plane. So let's go ahead and see if we can graph this. Well, we can graph this by basically changing t squared minus 1 and t into terms of x and y. So if we do that, x is going to be t squared minus 1 and y is t. But if y is t, I can plug y back into the x equation. So we're going to get that x equals y squared minus 1. So that's going to be a parabola, but it's a parabola which opens up to the right because the square is on the y instead of the x. So it's going to be a parabola which opens to the right and looks like it's got an x-intercept of -1. So back here. So it looks like it's going to do something like this. Whoa, that was bad. Okay, that's a little better. It's going to do something like that. And then we can obviously figure out the direction of motion. If we were to take t to be 0 and plug t equals 0 in, you get -1, 0, which is this point right here. That's where t equals 0. And then if we take t to be 1, well, we already found that, but that we found the velocity and acceleration, at 1. T equals 1, we're going to get 0, 1, so it's right here. So we are moving in that direction. And I'm actually not going to put arrows near those points because we're going to be doing some other stuff specifically at t equals 1. So that's where t equals 1. And then we have the velocity, which is the derivative, so it should be something which is tangent to this curve. So the velocity at 1 is 2, 1, so that will be right 2, up 1. So it probably looks like something like this, which makes sense because, again, it should look like it's tangent to the curve. And then we have the acceleration, which is 2, 0. That's going to be to the right, straight 2 units, just like that. So this one would be your acceleration at 1, and this one right here was our velocity at 1. All right, and hopefully that makes sense as far as how it works out there. The velocity, once again, is tangent to the curve, and the acceleration, what you can kind of think about the acceleration there is the acceleration is really, it's the rate of change of the velocity vectors, and the velocity vectors are going to be, looks like the first one, like if you did a velocity vector at t equals 0, well, then you would just get 0, 1, which would actually be, yeah, we'll use the same color, which would actually be something like that. What you can see is the acceleration basically is showing you that the change of the velocity vectors looks like the velocity vectors are starting to flatten out. So it went from completely vertical to something which is slightly more angled with v of 1, and then if you did v of 2, it's going to be even less steep. The acceleration is the rate of change of those velocity vectors. So it really does show that they're flattening out. Again, good conceptual stuff there. Okay. All right, let's go ahead and look at another example. Find the velocity, speed, and acceleration of r of t. Again, the process of doing this using calculus and algebraically is not too difficult. I want to kind of take a look at the graph of this one as well when we're done. So let's go ahead and start off by finding the velocity, which is going to be, let's see, what is that, cosine t, 1, negative sine t. And we want to do this when t equals 0, so the velocity at 0, cosine of 0 is 1, 1, sine of 0 is 0. So we get 1, 1, 0 for our velocity at 0. Let's find the acceleration. So the acceleration is derivative of velocity. Let's see, cosine t derivative is negative sine t. Derivative of 1 is 0. Derivative of negative sine t is negative cosine t. And again, we want to do this at 0. So we're going to get 0, 0, negative 1. And then we'll find the speed, which is the magnitude of velocity. So that's going to be cosine squared t plus 1. Squaring the negative sign is going to give you plus sine squared t. So underneath of that radical, you've got a cosine squared plus sine squared. So that's 1 plus 1 more is the square root of 2. So the speed at 0 or the speed anywhere, it looks like on this thing, is going to be the square root of 2. All right, so let's go ahead and take a look at what this looks like. You should notice that we've got a sine t, a t, and a cosine t, which means that this thing is going to be a helix. Now this time the t is in the y component, so it's going to be a helix which wraps around the y-axis. So let's figure out where we're going to start. So if we start at t equals 0, sine of t is 0, so x is 0, y is 0, cosine the z part is 1. So it looks like we're going to start up here on the z-axis, and then which way are we going to end up rotating this thing? So if we go to t equals pi halves, so that would be, let's see, sine of pi halves is 1, so the x value is going to be 1, which means it's going to come down this direction. So it's going to wrap around in this manner, something like that. And again, I'll go ahead and put the arrows on here indicating direction. It's actually harder to do than I thought it would be, keeping my arrows going the right way there. Okay, so let's take a look at this, because again, this is where some of the physics, those of you guys who know physics are probably going to already kind of know where this is going, but if we take a look at the velocity function at 0, the velocity function at 0 is 1, 1, 0. That's the vector we have. So that's 1 in the x direction, 1 in the y direction, but nothing in the z direction. So it basically stays parallel to the xy plane. So 1 in the x direction, 1 in the y direction, but nothing in the z direction. So it went out this way. 1 in the x, 1 in the y, 1 in the z. I did not really sketch that very well. Let me try that again. I think my dots are not in a good spot there. So let's do this. It's going to look more like this. And while I know that that doesn't look like it is parallel to the z, we're going to see if we can make it that way. So it's 1 in the x, 1 in the y, and then parallel to the z. Not the best, but it's supposed to be parallel to the xy axis. But probably the more interesting one is the acceleration, and that's an easy one to draw. That's 0, 0, negative 1. So from here, that is simply down 1 unit. And the reason that that's interesting is because this helix is basically circular. Other than the fact that it's stretching along the y-axis, it is a circular motion. And for those of you guys who know anything about physics, the acceleration of something which is going in a circular motion tends to point towards the center of the circle. Okay, and that's actually the centripetal motion portion of this stuff, which is going to come up later. But that's kind of what the interesting thing is there. So if you knew the physics behind this, you would have known the acceleration, because it's really a circular motion. It's going to point straight towards the center of the rotation. Okay, let's go ahead and look at the next one. A little bit different. This time it says find the velocity and position vectors of a particle that has the given acceleration and the initial conditions that a of t equals k, v of 0 equals I minus j, and r of 0 equals 0. So now we're starting off with the acceleration. And the acceleration is that a of t equals k. Well, k is obviously the z component, so it looks like it's going to be a 0, 0, 1 vector. That's what a of t is. So if I want to find v of t, that means we have to take antiderivatives, or we're going to integrate. So we start off by taking antiderivatives. So we're going to take the integral a of t dt. All right, so if I take the antiderivative here, I'm going to end up with some kind of a constant. I'm going to call it c1. I'll end up with another constant. I'll call c2. And then the last one, I'm just going to end up with t plus a third constant, c3. That's our velocity function. But we have to find those values of c. But it does give me an initial condition. It tells me that the velocity has to be, the velocity at 0, has to be I minus j. All right, so there are a couple different ways you can look at this. I mean, some of this might be very intuitive to you, but for those who it's not, I'm going to go ahead and make sure that we write it out here. So the C1 component says that, well, that component, the x component C1, has to equal the I component when t is 0, but there's no t's to plug anything into, and the I component has a coefficient of 1, so C1 just equals 1. C2, which is the y component, has to equal the j portion. Well, that's going to be -1, because again, there's no t values to plug anything into. The last one's a little bit different. We've got t plus C3, that's the z component, has to equal the z component of the velocity, but there's no z component there, so that's 0. And when I plug 0 in for t, we simply get that C3 equals 0. So now we actually can write our velocity function at this specific initial condition, which is going to be 1, -1, and then t. Okay, that's the velocity function for our given initial condition. But we also want to find the position vector, which means we're going to integrate this one. So let's go with blue. We'll take the integral of the velocity, which is going to be t plus, and you can go with, whatever c's you want to. I'm just going to keep on going. C4 -t plus C5, and then 1/2 t squared plus C6. That is going to be your position function. But again, we're given some initial conditions, so we can go ahead and figure out the actual position. So let's see. We were given that r of 0 equals 0. So again, if we want to put this information over here, we know that t plus C4 has to be 0. Specifically when t is 0, which means that C4 equals 0. We know that -t plus C5 has to equal 0, specifically when t is 0. So C5 also equals 0. And as you might guess, 1/2 t squared plus C6 has to equal 0 when t is 0. So C6 also equals 0. Now, obviously, you have to be careful because all of these things where we had t and -t and 1/2 t squared are polynomials, that you had some exponentials or something in there, plugging in 0 is going to give you something other than 0. So you do have to be careful, or if you had some trig functions or something like that. In this case, we have found now our r of t. R of t is going to be t -t 1/2 t squared for our specific given conditions. So again, just be careful on what functions you're given there. All right, we'll come back with our second video and start talking about centripetal force.